Imagine looking down at a surgical scar, right? Like a scar you had for a decade. It's completely healed, solid tissue.
Right, it's just part of your skin at that point.
Exactly. But then, over the course of just a few weeks, that scar simply starts to dissolve.
Which is a terrifying thought.
It really is. The tissue just gives way, and the skin opens back up into a fresh, bleeding wound. And you didn't injure it again. You didn't, suffer any new trauma. The spontaneous melting of your own flesh is happening simply because you stopped eating one specific type of nutrient.
It sounds like the premise for some kind of body horror film, honestly.
Yeah.
But it is a very real, heavily documented biochemical reality. Because, we tend to view the human body's structural integrity as permanent once it's built, like a house.
Right. You put the bricks in, they stay there.
Exactly. But the truth is, your physical scaffolding requires this constant active chemical maintenance at a microscopic level just to keep you from literally falling apart.
Well, welcome to the deep dive, everyone. We are taking that terrifying concept and using it to launch our mission today. It's a highly specific mission, but one that's universally relevant to every single person listening. We want to know, can vitamin C intake actually support collagen formation?
And to truly answer that for you, we have to completely deconstruct how we view this molecule. We need to look way past the generic health claims on the vitamin bottles and get down to the actual cellular mechanics.
Which is exactly why we've gathered this fascinating stack of sources for you today. We're pulling from systematic medical reviews, deep dive biochemical papers, and even modern clinical wound care guidelines. And I mean, what we're finding in these sources completely flips the script on what you probably think this vitamin does.
Yeah, because when you hear vitamin C or ascorbic acid, your brain is probably trained to think of like orange juice or winter colds.
Oh, totally. Generic immune support. That's the marketing.
Yeah, right. And the immune aspect is definitely what made it famous. But when you look at the raw biochemistry presented in these papers, its most structurally vital, non-negotiable role in the human body is something entirely different. It acts as a microscopic mechanic for your connective tissue.
Okay, but before we can even begin to explore how vitamin C builds that connective tissue, that collagen, we actually need to take a step back. We need to look at why we have to eat it in the first place.
That's a really good point.
Because as I was reading through these evolutionary biology sources, I realized that in the animal kingdom, humans are the weird ones here.
Oh, we are extreme outliers.
Yeah.
If you look at most mammals, dogs, cats, cows, bears, they synthesize their own vitamin C.
Wait, so my dog is just making it?
Yeah, they don't need to eat it at all. They produce it internally, right in their livers, starting from D-glucose. It's this automatic, continuous internal manufacturing process that just runs 24/7.
But humans somehow missed out on that internal factory.
Well, we didn't miss out, we actually lost it. Humans, along with higher primates, fruit bats, and interestingly enough, guinea pigs, share this very specific ancient evolutionary quirk.
Guinea pigs. That's so random.
It is. But millions of years ago, our ancestors developed a genetic mutation. You have a non-functional gene for an enzyme called gulonolactone oxidase.
Okay, let's unpack this. Gulonolactone oxidase. What exactly is that enzyme doing in a dog's liver that it isn't doing in ours?
So think of vitamin C production as an assembly line, right? With several specific steps. That enzyme, gulonolactone oxidase, is the absolute final worker on that assembly line.
Okay.
Because our blueprint for that specific worker is corrupted, the final step just never happens. The entire manufacturing line shuts down. We cannot make a single endogenous drop of vitamin C ourselves.
Wow. So, I have to ask you, because of one broken enzyme in our evolutionary past, we are permanently tethered to dietary vitamin C just to survive.
Basically, yes.
Just to keep our physical bodies from falling apart. Like a single genetic typo makes us lifelong dependence on environmental sources, like citrus and broccoli and berries.
That is the harsh reality of our biology. We are entirely dependent on exogenous dietary sources. If we don't ingest it, our internal supply drops to absolute zero.
That feels incredibly precarious. So assuming we do eat our broccoli and citrus, how does the body handle this molecule once it's inside? I have to imagine, since we can't make it, the body doesn't just let it float around aimlessly in the digestive tract.
No, not at all. The body treats ascorbic acid like precious, heavily guarded cargo. Once you ingest it, it doesn't just passively seep into your blood, it's actively hunted and absorbed in the distal small intestine.
Meaning the lower, far end of the gut.
Yes, exactly. Down there, the body uses these highly specific sodium-dependent transporters to pull it in. They're known in the literature as SVCT1 and SVCT2.
Wait, so these are just passive doorways. These are dedicated cellular transport systems whose sole job is to grab vitamin C.
They are active biological pumps. So SVCT1 is primarily responsible for pulling the vitamin out of the digestive tract and into the bloodstream. And interestingly, it's also highly active in the epidermis of your skin.
Oh, wow. Okay.
And then you have SVCT2. This transporter's job is to pull the vitamin from the blood into highly metabolic tissues. It actively pumps ascorbic acid into your brain, your adrenal glands, your leukocytes.
Which are the immune white blood cells, right?
Right. And crucially for our discussion today, it pumps it directly into your connective tissues.
So the body is hoarding it, basically, pumping it into the cells that need it most. But I want to bridge a gap here for you, the listener, because we've traced the path from eating a grapefruit, right, to absorbing it through these SVCT cellular bouncers. But what is the exact mechanism that connects this floating dietary vitamin to the physical, solid scaffolding of our bodies? How does vitamin C equal collagen?
To cross that bridge, we had to zoom way, way in. We need to leave the macro level of the human diet and enter the micro level of the cellular machinery. Let's look at the structure of collagen itself.
Okay, let's do it.
Collagen isn't just a random, unstructured blob of protein. It has a highly specific, very rigid architectural design. It forms a triple helix.
Like DNA. Because most people know the DNA double helix. So this is 3 strands.
Similar in its twisting nature, yeah. It's 3 separate protein chains wound tightly around each other to create a very strong fiber. And the sequence of amino acids, the building blocks in those chains, is highly repetitive. It's characterized by a recurring sequence known as the GlyXY sequence.
GlyXY, so it's almost like a biological stutter. Glycine, and then 2 variable slots over and over again.
That's actually a great way to picture it. Glycine is always that first position because it's the smallest amino acid. It's the only one small enough to fit into the tightly packed, crowded center of that triple helix without distorting the shape.
Oh, that makes sense.
The X and Y positions can vary, but the X is very frequently the amino acid proline. And the Y position is where our story gets critical. The Y position is often an amino acid called hydroxyproline.
Hydroxyproline. I'm guessing by the name that it's a modified version of proline.
It is. And this modification is the entire crux of human structural stability. When your spiralized cells, your fibroblasts, are building these collagen chains, they don't just grab a pre-made hydroxyproline molecule off a shelf. They build the initial chain using regular, standard proline.
But if they just leave it as regular proline, what happens? Why go through the effort of modifying it after the fact?
Because regular proline isn't chemically sticky enough, for lack of a better term. If you try to build a collagen triple helix out of just regular proline, the resulting structure lacks thermal stability.
Thermal stability. Wait, are you saying human body temperature is too hot for normal collagen?
Exactly. Without specific modifications, the collagen triple helix would literally denature. It would melt and fall apart at 98.6 degrees Fahrenheit.
That is wild.
Our normal body heat is entirely hostile to unmodified collagen. So to make the structure stable and strong, specific proline and lysine residues on those newly formed chains must be chemically altered. They must be hydroxylated.
Meaning the cells have to physically attach a hydroxyl group, which is an oxygen and a hydrogen atom, to the chain after it's already been built, just to keep it from melting.
Yes, this post-translational modification is mandatory, and it's performed by 2 highly specific biological workers. They are enzymes called prolyl-4 hydroxylase and lysyl hydroxylase.
And I'm going to take a wild guess here. These enzymes need our missing vitamin to do their job.
You're on the right track, but the actual mechanism is brilliant. What's fascinating here is these hydroxylating enzymes belong to a larger family called 2-oxoglutarate-dependent dioxygenases.
That is a mouthful.
Yeah, in the biochemical literature, they just call them 2-OGDDs to keep it simple. But at the absolute dead center of their active working site, these enzymes hold a single atom of iron.
Wait, a single atom of metal is running this complex protein modification.
That iron atom is the catalytic heart of the enzyme. For the enzyme to successfully attach that hydroxyl group to the proline and lock the collagen into a stable state, that iron atom has to be in a very specific electrical condition. It must be in a reduced ferrous state, which chemists label as F2 plus Et.
Okay, if F2 plus Et. So the iron is primed and ready to work.
But every time the enzyme completes a reaction, every time it hydroxylates one proline molecule, that iron atom loses an electron. It undergoes oxidation. It shifts from its working ferrous F2 plus state into a ferric state known as F3 plus hair.
So the chemical effort of modifying the collagen literally changes the charge of the iron atom, and I assume F3 plus is not a state we want it in.
No. When that iron atom flips to F3 plus air, the enzyme goes completely dead. It freezes up. It cannot hydroxylate another proline molecule. It cannot stabilize any more collagen until that iron atom is handed an electron and restored back to F2 plus B.
Okay, so let me try to picture this. Imagine collagen is a tightly braided rope, right? And the 2-OGDD enzyme is the complex braiding machine making that rope.
Okay, I like that.
That machine runs on a central iron gear. As it braids, the chemical friction causes that gear to rust. It oxidizes into F3 plus, and the machine violently jams. You need a highly specific lubricating oil to strip the rust away, turn the gear back to F2 plus A, and let the machine keep braiding. Vitamin C is that oil.
That is the perfect visualization. Vitamin C ascorbic acid is a master electron donor. The sources call it a reducing co-substrate. It steps into the active site of that jammed enzyme, hands an electron directly back to the rusted iron atom, reduces it from F3 plus back to F2 plus S, and instantly reactivates the braiding machine.
Wow. That completely reframes the idea of a vitamin. It's not just a generic building block like a brick. It's the mechanic keeping the machinery running.
Precisely.
So what happens to the human body when the mechanic vanishes? Like if you remove the lubricating oil entirely and every single one of those braiding machines grinds to a halt.
The macro consequences of that microscopic failure are horrifying. This biological jam is the exact pathology of a disease that has haunted human history, which is scurvy.
Scurvy. I mean, I think most people hear that word and immediately picture pirates or historical cartoons. It doesn't feel like a modern medical reality.
It's often dismissed as a historical artifact, but the physical horrors of scurvy are just the visible manifestation of your proly-hydroxylase enzymes shutting down. Because without ascorbate to donate those electrons, your fibroblasts don't just stop working. They keep trying to pump out collagen. They're still manufacturing the protein chains.
But because the braiding machine is rusted out in that F3 plus state, they are pumping out underhydroxylated chains. They are manufacturing defective rope.
Defective, weak, unsticky rope. The collagen completely loses its tensile strength. The triple helices degrade almost as soon as they are formed. Now consider where collagen is most critical in your anatomy. It is the primary structural component of your blood vessel walls, specifically the delicate capillary basement membranes.
Oh, wow. So if the collagen supporting your capillaries is defective, the pipes just burst.
They become incredibly fragile. The sources describe the classic progressive symptoms. It starts with perifollicular hemorrhage, which is spontaneous bleeding around your individual hair follicles.
Just from normal movement.
Yeah, and then comes severe deep tissue bruising from just existing.
And the teeth. Because that's the famous symptom everyone knows, right?
Right. Your gums have an exceptionally high turnover rate of collagen. Because they can't rebuild that tissue, the gums begin to swell, turn black, and physically degrade. The periodontal ligaments holding your teeth into your jawbone literally dissolve, leading to severe dental mobility. Basically, your teeth fall out.
And this brings us right back to that horrifying scenario from the beginning of the show. The scars melting.
Yes. Because structural collagen is required to maintain scar tissue, a severe vitamin C deficiency causes old, seemingly permanent wounds to spontaneously break open. The tissue holding the scar together simply melts away.
Here's where it gets really interesting, though. The history in these sources is wild when you view it through this biochemical lens. They bring up James Lind and the British Royal Navy during the Age of Discovery in the 1700s.
Oh, the linings.
Exactly. Ships crossing the ocean were losing more men to scurvy than to actual naval combat. And James Lind conducts what is widely considered one of the first controlled clinical trials in history. He figures out that giving sailors a ration of citrus fruit cures the disease.
By earning the British sailors the historical nickname limes because of their lime juice rations.
But the irony is staggering. They had absolutely no concept of what a vitamin was. They didn't know what an electron or an enzyme was. They were biochemically treating a massive prolyl hydroxylase deficiency at the subcellular level centuries before anyone had even proven that cells existed.
It's a phenomenal example of clinical observations succeeding despite a total lack of biochemical understanding. They observed the what, but it took science another 200 years to finally uncover the how and the why.
Yeah, and it's easy to look back at the 1700s living on hardtack and salted pork and think, well, we've got grocery stores on every corner now, scurvy is solved. But when you look at the modern clinical sources in our stack, they paint a very different, very concerning picture.
If we connect this to the bigger picture, the clinical data from Australia highlighted in our sources is particularly alarming. A 2018 study analyzed a cohort of adult patients attending a standard metropolitan surgical practice. They weren't looking at pirates. They were looking at modern citizens.
Hmm.
And they found that 21.4% of these surgical patients were clinically deficient in vitamin C.
Over 1 in 5 surgical patients. That is terrifying if you are a surgeon about to cut into someone's tissue, knowing their body lacks the fundamental molecule required to stitch that tissue back together.
And it gets much worse when you look at specialized populations. Another study reported a staggering 50% deficiency rate in a high-risk chronic foot ulcer clinic in Australia. Half of the patients walking through the door with severe non-healing wounds lacked the essential electron donor required to fix them.
Wait, why is the deficiency rate so incredibly high in these specific wounded populations? Is it purely a diet of ultra-processed food, or is something else happening?
Diet is definitely the foundation, but there is a dynamic metabolic process at play here. Remember how we discussed that vitamin C isn't just a passive catalyst?
Right, it donates its electron.
Exactly. It gets consumed in the reaction. When you have a massive wound, a severe infection, or you undergo major surgery, your body mounts an aggressive inflammatory response.
And inflammation creates a massive amount of oxidative stress at the cellular level.
Precisely. Because vitamin C is also a potent antioxidant, that local inflammation rapidly accelerates the degradation and consumption of ascorbic acid at the actual wound site. Your body burns through its local supply at an astonishing rate. If you go into surgery with a low baseline from a poor diet, and then the trauma of surgery consumes what little you have left, your local vitamin C levels plummet to zero.
Your collagen braiding machine runs completely out of oil at the exact moment it needs to be running overtime.
So in modern clinical wound care, targeted supplementation has become a vital tool. The molecular studies in our sources demonstrate that providing adequate vitamin C directly increases the messenger RNA levels for type I and type 3 procollagen in human skin fibroblasts.
So it's essentially sending a louder, clearer genetic signal to the cellular factory floor, telling it to ramp up collagen production.
Yes. Systematic medical reviews now strongly recommend clinical vitamin C supplementation to accelerate the healing of notoriously difficult wounds, like severe pressure ulcers, bed sores, and chronic diabetic foot ulcers.
I want to clarify something crucial here, though, because it's easy to hear all this and think we found a magic bullet. Can someone just down a massive bottle of ascorbic acid pills and suddenly gain Wolverine-level healing powers and perfect wrinkle-free skin?
That is a vital distinction to make. No, it is not a solo miracle worker. The biochemical reality is that while vitamin C is an absolute biological necessity, the non-negotiable lubricating oil, you cannot build a house with only oil. Combinations of nutrients are what actually dictate successful healing.
Right, you can't just isolate one variable and ignore the rest of the assembly line.
The clinical guidelines from the sources emphasize that vitamin C is a critical cofactor, but it is routinely deployed alongside other essential micronutrients. Clinical trials often use specific combinations, like they supplement vitamin C alongside zinc, which is fundamentally vital for cellular proliferation and managing the immune response at the wound site.
And I saw copper mentioned in the sources as well.
Yes, copper is required for another enzyme that cross-links the collagen fibers together to give them final structural rigidity. They also supplement with amino acids like arginine.
Because if you have all the lubricating oil in the world and all the active enzymes, but you don't have the actual raw protein substrate, the literal chemical threads to braid the rope, you still aren't building any collagen.
Yes, exactly. Baseline testing to identify specific deficiencies, followed by targeted balanced nutritional support, is the scientifically validated approach. Throwing mega doses of vitamin C at a complex wound won't magically heal it if the patient is severely deficient in dietary protein zinc or, the iron needed for the core of the enzyme itself.
So what does this all mean? We started this deep dive with a very targeted question. Can vitamin C intake actually support collagen formation? And exploring these sources has given us a resounding, scientifically verifiable yes. But it's so much deeper than the generic word support implies. Vitamin C isn't just floating around offering good vibes to your skin. It is the literal essential key that unlocks the specific 2-OGDD enzymes responsible for building the physical scaffolding of your existence.
It is the electron donor that rescues your connective tissue machinery from oxidative death. Without it, the machinery rusts, stops, and the tissue fails. But before we wrap up, there is one final, truly mind-expanding concept hidden in the broader context of these biochemical papers that I think you need to hear.
Oh, lay it on us. Where else does this rusted gear mechanism show up?
So we spent this entire time talking about how vitamin C is the mandatory cofactor for the 2-OGDD enzyme family, specifically focusing on prolyl hydroxylase, the builder of collagen. But the sources reveal a fascinating biological twist. Prolyl hydroxylase is not the only 2-OGDD enzyme in the human body.
Wait, there are other enzymes using this exact same iron core machinery?
Many others, and one of the most profoundly important is a group called the TE family of enzymes. That stands for 1011 translocation enzymes. These TE enzymes are structurally 2-OGDDs. They have that exact same iron atom at their core.
No way.
Yes. They require the exact same electron donation from vitamin C to function, but their job has absolutely nothing to do with building collagen.
If they aren't building structural tissue, what is their function?
They operate deep inside the nucleus of your cells. They act as epigenetic erasers. Their primary role is to hydroxylate a very specific molecule called 5-methylcytosine, which is attached directly to your DNA.
Whoa, hold on. They are physically editing the DNA.
Well, they aren't changing your core genetic code, but they are altering the epigenetic tags, the chemical markers attached to your DNA. These markers act like microscopic volume dials, controlling which of your genes are turned on and active, and which genes are turned off and silenced. And just like the collagen-building enzymes, if these KET enzymes don't get vitamin C, their iron atom rusts into F3 plus beer, and they stop editing your epigenetics.
That is a staggering implication. If vitamin C is the chemical switch that allows enzymes to build the structural collagen holding your body together, and those exact same types of enzymes are responsible for editing the epigenetic dials on your DNA, could your daily intake of vitamin C not just be holding your physical tissues together, but actively shaping the genetic expression of your very cells?
It completely revolutionizes how we view nutritional biology. A molecule we write off as a simple cold remedy is actually a master key for both structural integrity and epigenetic regulation.
It goes from being a simple building block to the master mechanic of your cellular destiny. Thank you for joining us on this deep dive. Keep asking the hard questions, keep looking past the surface level, and we'll see you next time.